Well, I don't know how the microphone is, but I will still teach to who's here. Um, so we switched now to the third culture, which is Greek math, and you could actually do an entire course just on Greek math. You could do a full year on it. It's that much. They just got to the point where we have it all. We have thousands of pages of Greek math. So my first question is, what do you already know about Greek math? Can you name? Because in the other, hi there. What's your name?
Janet.
Janet. Okay. That's it. That. So unlike the other cultures where you hadn't heard any of those names, like I didn't give you any names from Babylonian or Egyptian math. And sometimes they like the name of the scribe, but he's not the one who invented the math. But in Greece, we start getting people that we can attach their names to. So can anyone name one Greek mathematician that a name is just in pop culture? Any names?
Euclid?
Okay, so we have Euclid as one. No.
I could give you a philosopher.
Oh, you know what? A lot of those philosophers.
Yeah, and
Aristotle.
So they all did a little bit of math, like Plato. They say that in the school, it actually said on top in Greek, but this is Muhammad. Okay. That's okay. That's okay. You'll know now how long it takes in the worst case. So Plato did some math, but apparently over the Plato Academy said let only people who are knowledgeable of geometry enter here. But so Euclid, other Greek mathematicians. There's about two others that are like household names in my mind. Euclid's a good one though. We're doing most of Euclid today. But any other Greek mathematician names? And I think that there's two in particular that you'll say, okay, I've heard those names before. Well, I will tell you, Pythagoras.
Oh.
I wondered, but I wasn't sure.
Yeah. So you might know Pythagoras here, but not know that he was Greek. And then, really, the greatest of all. Is Archimedes.
Oh.
And he's sort of, I don't know, in every household, a household name, but that's a pretty famous name, Archimedes. It's funny, Euclid.
Is that where Ark comes from?
Ark, no, I think Ark was around before, but there's a lot of stuff named after Archimedes. There's actually streets. There's a street in Brooklyn. One of the subway stops is Euclid.
Euclid Avenue.
So there's streets named after mathematicians. I don't know if there's any. So that's kind of interesting. Archimedes recently showed up in a movie. I don't know if anyone saw it or not, but it was the fifth Raiders of the Lost Ark movie. Did anyone see that one? Indiana Jones. And
Not a fan.
No, I don't like that one. Not even the first.
I don't like Indiana Jones.
Not even the first one.
Not a fan.
Did you watch the first one, or did you just watch the sequels?
No, I'm just not a fan of it.
So in the fifth one, which was not such a good movie, the actual plot was that there was a mechanical contraption that Archimedes made, and it enabled him to go back in time and meet Archimedes. So it was kind of neat to see that Archimedes made an appearance in a popular movie. So here are the three most popular names of Greek mathematicians. Pythagoras. There's a lot of legends about the different mathematicians and things that they did, how smart they were. But a lot of these things, at least for Pythagoras, are sort of legendary because Pythagoras he died and his students kept making new math, and anything they made, they just put his name onto it. So,
Is that how we got the theorem?
Pythagorean theorem, although it was around way before him, but it got named after him. So here's a couple of names. Oh, so I threw in 2 other names just to like.
Or Apollo. That's why they named the NASA ship Apollo.
Oh, I wonder, why, the Apollo, Apollonius. I don't even know what, literally what some of these. Ah, good. Okay, so who we got? We got Stephen and Stephen and. Okay, good. Okay, so all we've done so far is start talking about Greek mathematicians and some of the famous ones. There are a lot more, but this is a good sort of group here because Thales goes back and Pythagoras is back in 500 BC. Euclid is 300. Archimedes is after Euclid, and Apollonius is after Archimedes. And these people did so much, especially Archimedes and Apollonius. They evolved the geometry so far that for thousands of years, people really just built on what they did, reproved it, explained it. Like these things, their documents became just like the things that everyone just thought were like some sort of a perfection. Now, we're going to start with Thales. Thales wrote the first, it's not really a book, but he put down 5 geometric theorems, or five properties of geometric figures. And I'm going to tell you what his 4 of his 5 things. Let's wrote these down. Now, a lot of you haven't done geometry in a long time. And that's why today is sort of an overview of geometry and stuff to think about. There's really no numbers. Maybe we like calculate out an angle or something like that. But there's a lot of logic in geometry and there's a lot of visualizing that actually does challenge people a lot. Even seeing 2 triangles where one of them is like rotated a little bit. It's hard, and you teach the younger kids, and the idea of, these 2 triangles are congruent, that's not so obvious. That's why it's good with all these manipulatives. You hand the kid 2 triangles, and you say, can you put one on top of the other so it covers it exactly? But when it's drawn on paper, it's not easy. You take a triangle, rotate it, it's hard to see, or you put it backwards or something. So geometry is not that easy. Reflecting it. So it's not that intuitive. It can be kind of challenging. But here are some Thales theorems. Here are, you know what, this pen is too thick. I don't know if you guys use smartboards or not. Mm-hmm. They are pretty good contraptions.
Well, they've upgraded them.
Yes. Hold on, why keeps going back to that. There we go. So one of Thales' theorems is that if the 2 sides or if you have a triangle, 2 sides are equal, isosceles triangle, I'm going to, I'll make those markings, mean the 2 sides are equal to each other. And you probably know what else is going to be true about this triangle, besides that those 2 sides are equal.
2 angles equal.
That's right. And specifically these 2, so I'm going to use a different color for that to illustrate. The black is the thing that we're told is true, and the red is the thing that is also true. And it's actually very hard to prove that. It seems such an obvious thing if we see these triangles and these angles look equal to each other. But actually proving that is actually pretty hard. So prove it, not just here's a triangle, I measured a bunch, but like a geometric proof that stands the test of time, that no one will ever make a triangle that has 2 sides equal and the 2 other angles aren't equal. You know, it's hard to prove something. You can make millions of copies of triangles, but that doesn't prove it. All someone has to do is show you one counterexample, and that theorem goes out. You know, it's not true anymore. But that's one of Thales' theorems that he put down. A second Thales theorem is that when two lines intersect, big letter X, what conclusion can you make?
Opposite angles are equal.
That's right. Now, when you say opposite, what's a more accurate word of that? They are opposite, pointing at each other. What's the geometric word for how to describe those angles? Does anyone know? Is that? Oh, they're not alternate though. They're called vertical angles. So we'll have some vocabulary, a reminder. Isosceles triangle, and this is vertical angles. And I'm just going to give you the smallest collection of theorems that we need so that tomorrow, we do Greek geometry for 4 classes. It's like a third of the course is Greek.
Why you say tomorrow?
Oh, the next big class phase. We just do a lot of Greek math, and the vocabulary is going to be useful. It was actually not easy to create this sequence of lessons because it's not just going to be, we're going to learn the first 2 weeks of geometry in 4 days. It's not that. I want to go way beyond what you might have ever learned in geometry. But I have to give you this collection. And so far, I hope you're not feeling, I spelled vertical wrong there. I left off the, this one goes like that. Okay, the third one is this. Actually, I'm going to make the third one, I'm going to switch my order around. What I'm going to call the third one is going to be a kind of funny one. And this is one that you will not be aware of already. The first two you might say, okay, I remember those. So the third one is, if you have a circle, and you make a diameter, and you put a point anywhere on the top half, the semicircle, and then you make a triangle like that. There's something special about that triangle, which is not something that you will it's not something that you'll know, most likely. Let me come over here. This is pretty cool. Desmos, they have the ability to make. So here, I'll make a point. Oh, how do I, that's funny. How do I turn off? Oh, I'll just have to do that this way. So, whoops. Let me just get, what is that? Some kind of, okay, so here's a point. Actually, yeah, here's a line segment. This is called dynamic geometry software because you get to move it around. Anyone use one ever? What's the most famous one now? Just the free one. GeoGebra. Yeah, so there's a website called GeoGebra that lets you do this. This is desmos.com/geometry, and it's kind of neat. GeoGebra is a lot more powerful, but this one's actually pretty good if you just try to do something really quick. Now I want the midpoint of this. Now the question is, how do I get the midpoint? I forgot how to, hold on a second. midpoint. So you click on the line, and what's neat about dynamic geometry software is I have this point here, and watch when I move, see when I move the line around, that point will stay as the midpoint. So I didn't just put it randomly there, but it's constructed as the midpoint, so it's always the midpoint. Then I make a circle. I click on the center points I want. Go like that. Actually, if you brought your compass with you and you want to make a circle, if you brought one, you can make a nice circle in your notes. I should have done that. And let's say you just purchased one. And how much did that go for?
It was $1 and change.
$1. And it's funny that they're selling them. I would imagine that you're the first person to buy a compass down there in like a long time. Well, maybe not. No, I said, yeah, I would stand by. So everyone draw a circle on their page. Now on an iPad, you probably have a way to. There's probably a circle drawing tool of some sort. Yeah, so draw yourself a circle, and when you draw the circle, make sure you know where the center is, because when you draw it, the little pointy part of the compass will make a little hole that becomes the center. By the way, there's a website that's called mathspad.co.uk, and it's pretty neat because check out what I can do. I can just I go like this, see, make a nice circle like that. Anyway, I'm now going to take a point, and also what's neat about a dynamic geometry program is that if I make the point on the circle, now look, I can move the point around, but it stays on the circle. So that's neat also. And then I'll come here and make 2 more line segments. And I have a triangle. Now I can change the size, so I can see if something's true, is it always going to be true, or just for a... So it's kind of neat. I can actually move this around. Now look at the triangle on the screen now. Here, I'll make it... Is there anything that all these triangles have in common? Anyone have a suspicion about what it might be? It's not obvious really at all. They're all triangles, they all have 3 sides. But there's some property that no matter how much I move this point, every triangle I make has something in common. You know what it is?
Does it have to do with, how would you calculate the arc of the circle?
Oh, the arc? Okay, maybe. It won't have to do specific with the arc. Oh, and let me just think. I was taking attendance. Is that?
No, we got a little.
That's okay. Okay, great. That's all right.
Would it be that the
Yeah, what do you think, physician?
one side would always be the same length?
Well, certainly, yeah. This diameter is part of all of them, so that's something they have in common. Check this out. It is a right triangle. It doesn't look like, it looks like a right triangle, but who's to say it actually is a right triangle? Well, that's what we're going to prove. So this angle, it looks like a right angle. It's reasonable to think it's a right angle. In fact, if I come over here, and I go Thales theorem, this is GeoGebra. Here's this picture again. And you could actually see, I marked it. See, it says 90 degrees here. So that's very surprising. It's it looks like a right angle, but who's to say it's always a right angle? Well, that's called Thales theorem. Literally, there's a bunch of theorems that Thales, wrote down and all.
but this one specifically is very famous, so much so that it's called Thales' theorem. And what Thales' theorem, which is hard to say, says is that it's guaranteed for that angle to be a right angle. That's one of the things we're going to prove, actually, but for now, this is our collection of theorems.
I was going to ask how you proved it.
Yeah, that's coming. Now, I'm going to leave these three for now, and I'm going to switch. Hold on, I just want to make sure I want to say something. I want to. Okay, I'll just make sure that I don't tell you something inaccurate.
So the two vertical angles, they're equivalent, right?
They are, as are these other two.
Okay.
Okay, in order to prove Thales' theorem, we need to, there's another fact that I'm just going to throw in, and I'm not going to credit to anybody yet. What's the most famous theorem in geometry of all? Pythagorean theorem. What's the most famous property of triangles of all? Not just right triangles, but just
They equal 180.
they equal 180. If there's like one thing that to remember from geometry, it's that in a triangle, any triangle, if you add the three angles together, I'll just say measure of angle A plus measure of angle B is equal to 180 degrees. That is not like such an obvious thing, but if you taught almost any grade level, you would as a fun, here I'll just grab a piece of paper here. If you maybe you did this as an activity, students like they make a triangle out of paper somehow. Now this doesn't prove it specifically, but it's really fun. You see every student, makes a triangle, and then you go like this. You just rip off these two angles, and then you assemble them up here. I didn't do the best job on this, in fact, but when you put them together, they make like a puzzle where the tops become 180 degrees. Let me draw that out a little bit better. So if I take this angle here, and I kind of rip it off and put it instead up there, and if I take this angle here, oh wait, sorry, I went the wrong way there. I take this angle and rip it off and stick it over there instead. And I take this angle and I rip it off and I put it over here. See, those three pieces together make 180 degrees. So for instance, if this was 70 degrees and this was 60 and this was 50. And those three angles add up to 180 degrees. So that's an important theorem, and I'm going to accredit it later, or at least show a proof of it. But that's actually hard to prove also. Like, ripping a piece of paper doesn't prove that it's always true, that nobody is ever going to find a triangle in the world that where the angles only add up to 180. Like, just because all the kids in the class rip their things, but it still is. By the way, who taught Does anyone did this activity, those teachers? You did, what grade do you teach?
I teach high school geometry.
Okay, is that how you do it with the paper ripping? Yeah, that's classic lesson, you know, in geometry. There's only like a few times you ever get to really make a hands-on experience, and that one, to not do it would be negligent, so that's great. So let's not credit this, although this isn't officially one of the 5 Thales theorems, but it would be needed to do the proof. So now we have a collection. This is a small collection. Somehow, I want to just use the isosceles triangle, that the 2 base angles of an isosceles triangle are equal, and the fact that every triangle, the sum of the angles is 180 degrees. With those two, just those 2 tools. Not even this vertical angles isn't even going to be this vertical angles is not going to be a part of it. We're going to prove the third one, the Thales theorem. I think I want to throw in another theorem. And what's funny about this theorem, it's like it's like you don't really need this theorem, but I'm going to say it. So imagine I have an 80-degree angle and a 70-degree angle. And I were to extend this side a little bit. This is a question for everyone now. What would be the measure of that obtuse angle? So just you talk to people around you, just what do you think?
It will be 80.
It's not 80 though. So just,
Oh, no.
I'll make this, let me make my X a little better. So there's the, and it is. Why do you think 150?
Because the interior angle is 30 degrees and it's bisects. So then the difference would be 180 minus 30 would be 150.
Yes, so you could find the third angle because the angles add up to 180. 70 plus 80 is 150, so I'll write down 180 minus 150 equals 30. That's that angle. But then how do we get the 150 from there? Yes, you're going to say?
Subtract 180 from 30.
Yes, we also have supplementary angles. So 180 minus 30 gets me to the 150. Well, so we don't need a special new theorem to answer that question. But there is, notice how 150 is equal to 80 plus 70. And that has a name. It's called the exterior angle theorem. And what the exterior angle theorem says is that this angle, if I call this, I'll call this angle 1 and angle 2, that it's the sum of the other, they call these the remote interiors, meaning there's 3 interior angles, but this one's so close, it's not remote, it's close to the x, but the other 2, so I'll write x is equal to angle 1 plus angle 2. So with that theorem, you could have jumped straight to this answer. You could have just said, oh, it's 80 plus 70. Now, let's say it came up on it, what I saw on the homework, let's say. You don't need to use the exterior angle theorem on the homework, or on the final. If this question came up, it would be perfectly fine to say, I'll first get this 30. But I want you to know about the exterior angle theorem. So we have this small collection now, and geometry is about building up a couple of theorems, and they get used to prove more complex theorems, and those get used to prove more complex theorems. And so you end up with some geometry that's so hard that there's only a few people in the world that even understand it, which I'm not one of them when it gets too hard. Okay, we're now ready for our proof. So here I have this triangle. And when I teach high school, so a lot of times in my high school math and people teaching high school, people teaching college, they make things too abstract and think, oh, well, I proved this abstract case, so of course it's true. But I always found, even in high school, I teach at Stuyvesant High School, so it's like, top school in the city, and I try not to teach too abstractly, and this goes for every grade level. When you make it too abstract, it confuses people a lot. So what I'm going to do is actually write in an angle and say, what if the angle's 50 degrees, like specifically? Now you might say, well, that's not proving the theorem anymore. That's only proving it's true if it's 50 degrees, but it's going to help. And I drew in an extra line. I drew in a radius. That's you. In geometry, when you draw an extra line, there's a name for that. You're a high school teacher, you have that extra line. When you draw a new line into your picture, you know what it's called when you do that? They call it, it's called an auxiliary line. I'm reacquainting us with some of the vocabulary. Auxiliary line just means I had this picture and I drew in an extra line. If the theorem's true, it's still true. Drawing that extra line doesn't mess anything up, but that extra line might help us prove this theorem. The goal is to prove that this angle is a right angle. It looks like a right angle, but to prove it is hard, and that's why first I'm going to prove it generally. No, first I'm going to prove it specifically when there's when it's a 50-degree angle, and then I'm going to prove it generally when where the angle could be anything. So here's some questions for you. I'm going to put numbers in for like the order. I want you to answer these questions. 1. How big is that angle? Which is this that piece? Actually, that's a good question just on its own. What do you think? Is that possible? Is there enough information in this picture to establish the measure of that angle up there? Talk to the people around you.
Are we going on to the assumption that we don't know that the other angle is 90?
Right. We don't know it's 90. We're hoping to prove it's 90. So we don't know it's 90 right now.
Okay.
But we do know that this is definitely the center of the circle. This line is not just a random chord on the circle. It is a diameter. Okay? Any thoughts on what that angle is? You talk to your neighbors about is there any kids? Keep in mind, our toolkit is so small. We only have like 3 theorems to
I'm
use.
trying to see how would I predict the angle in the middle. That helps me because I know that there are other ways around the one. So, yeah.
I don't think there is like those two. We were at the center angle first, but we need to figure angle 1.
Okay, anyone know what angle 1 is? Now remember, our toolkit's very small. All we have is that in an isosceles triangle, the 2 base angles are equal. Vertical angles are equal. 180 degrees in a triangle, and the exterior angle theorem. That's all we have.
Maybe there's a-
We have 4 tools. That's all. So we must have to use those tools.
I think we figured it out.
Yes, what do you think it is?
Because the 2 sides are equal, so then 1 is 50, because then the angle is equal.
Yes. See, what was hinted at here is that this blue triangle is an isosceles triangle. Because, even though I didn't say it specifically, in a circle, by definition, every radius has to be equal to itself. All radii are equal in a circle. So it wasn't given, it didn't say, hey, this is an isosceles triangle. But because it's in a circle like this, every radius of a circle is the same length, because a circle is, by definition,
all the points that are the same distance from the center. So this ends up being an isosceles triangle,
which makes this 50 degrees. Next question. How big is angle number 2?
It's 100. Why is that?
It's supplementary, 80.
Oh, okay, yes. Okay, so you could work this out as 80 if you want, and then do supplementary. Or you could add 50 plus 50. It's up to you. And now, the big question. Angle number 3. We don't know already. We can't use, I know that it's 90 altogether. So what if I didn't know that? I can still get angle number 3. Talk to your neighbors. This is a really kind of a fun question. Now that I have the 100, it's kind of like each thing, it's like a mystery where each clue leads you to the next clue. How does the 100 help me figure out angle 3? Oh, do you know?
40.
What was that?
Because if angle 2 is 100,
Yes.
and it's an isosceles, those other two are equal to each other.
What's an isosceles?
The second triangle.
Yes. There is another triangle here, and it is also isosceles because, again, 2 of its sides are also radii. So it's really clever, this idea that, like, there's so many isosceles triangles in this picture, and that means that these 2 angles, whatever they are, equal each other. I'm going to put another 3 here. Angle 3, that is. But together, if these three angles have to add up to 180, 180 minus 100 is 80. That's the combined other 2 angles, but because they're equal to each other, each one is half. And 40 plus 50 is 90. So you say, okay, that's great. In this case, that angle ended up being a 90-degree angle. But if I change this to a letter, I'm going to use, I'll use, in this type of math, they're always using Greek letters, alpha. Only because the ABC letters, those are used to describe the points. So the angle, they usually use Greek letters for. It is a little confusing, but the alternative is to name the angle with 3 letters. I mean, like for this one, I could do 1, but for the angle in the middle, I'd have to use 3 letters. So using the Greek letter alpha, the main angles that the main letters we use are alpha, beta, and most famously,
Gamma.
Gamma can get used,
Omega.
but most famous to name an angle, at least, theta, which looks like. Theta is so common, it's almost like using letter X in algebra. Like, if they just need to call an unknown thing, they often use theta. So, check this out. If I change this now to just call it alpha instead of 50, then I get an alpha there also. Hold on a second. Oh, I have an idea. I think I like this even better. And I'm going to call this angle beta. That's a badly drawn beta. Which means this is beta up here. Now that doesn't prove anything yet. That's just proving me that this angle is the sum of those two. The top one is alpha and beta, adds up to them. But we don't know, what they are. But check this out. That angle, remember when it was 50-50 and that became 100? So now I'm saying alpha, alpha, 2 alpha, exterior angle. On the other side though, beta, beta, 2 beta. And now when we finish this up by saying, whoops, undo. These two things are supplementary. So I can say 2 beta plus 2 alpha is 180 degrees. We can see them right there. It makes a nice line there, the supplementary. And then how do I get to the conclusion? From here, I want to say that just alpha plus beta is 90. What lets me say that? Yes.
You divide by 2.
Divide by 2, yes. Divide everything by 2. So that is our first proof. And it's really ingenious how we started with just the fact that triangles add up to 180 degrees and that isosceles triangles have the 2 base angles equal. And from those 2 tools, we prove something that's like, in my mind, pretty surprising. There's that line drawn in. I like that out of full screen mode, go like that. And that's our first proof. That is the proof of Thales' theorem. So you might wonder, God, that proof is hard. Is the final going to have proofs? No, the final will not have proofs. This would be a final exam type question. That would be the whole question. Do you know that angle must be 90 degrees? The answer would be 90 degrees. So that would be an example of a final exam question. Another, just if you wonder, like, how do I think of questions? Another type of final exam question. Maybe I put a 50 here, and I put an X there, and just say, what's that angle? So it's like, I wouldn't say, prove Thales' theorem. I would say, I'd give you a diagram and ask you a really specific question with a numerical answer. And the idea is you'd have to, that would show that you at least, that you understood the different steps of the proof. Okay, so that's pretty good. That's our,
Back to that last page.
oh, this one? Yeah, what I'm showing you here is how do I make up the final? Like, what do I do? I think what's something that I could ask about that proof? Number one, conclusion of the proof, just knowing that. Because before today, that's a question you probably couldn't answer. But today, you can. And before today, I don't know, because you probably wouldn't think, oh, this is definitely an isosceles triangle. You wouldn't even know to look for that. Honestly, this wouldn't have been a bad final exam question. Just saying that, like, because if you don't know to look, like, oh, it's an isosceles triangle, you wouldn't know to even look for that. So knowing to even look for it is showing that you've learned some of the geometry in the course. Okay, what we have done is we have proved Thales' theorem. That's a big thing in geometry, because this is 500 BC, and the geometry was fairly primitive in the sense that they didn't really know that much. Yet, this is the very first kind of surprising theorem in geometry. And it's not that it's important either. it's really just for the sake of, like, they're doing, like, to them, Letitia mentioned philosophers, math and philosophy were very related to each other, like, we're proving truths about, like, the world, or about not just this world, but about the imaginary perfection, world of perfection, and what would be true, like in heaven, that sort of thing. That's what they're math. So this isn't about, like, oh, I need to know Thales' theorem because I'm building a bridge. This is just like some truth that we uncovered. And so they're really not thinking this needs to be practical. Okay, so now we've done Thales' theorem, puzzle or proof. Now I want to move on to the next mathematician. And this, I had Pythagoras listed, but I'm going to skip him and skip over to one of the most important names. Whoops, I should spell his name right though. Euclid. So Euclid, street name, in Brooklyn, I think. I see on the subway, I always think it's fun to see someone's going to Euclid Avenue. Like, that's a Greek mathematician from 300 BC. So Euclid was not so much a great mathematician as a great writer of books. And Euclid wrote, there were other people who wrote books about geometry building up to Euclid. But Euclid's book that he wrote was so good that they stopped making copies of any of the old ones, so that they're all lost. People talk about them sometimes. And not only that, it was so good that it was in continuous use from 300 BC until still today. Euclid, and the name of the book, and you maybe heard of it before, but the book that Euclid wrote, is anyone the same? I'll just say that it's called Euclid's Elements, or he called it The Elements. The Elements. Also, he called it The Elements, but we call it. Working well, thanks. Okay. It's also called Euclid's Elements now. And aside from the Bible, the New Testament, Euclid's Elements, that book, is the most published book in the history of the world. Euclid's Elements has been in continuous publication from 300 BC till today. You can go to Barnes & Noble and buy a copy of it. It was used as a textbook up until like the 1950s. That was your textbook, Euclid's Elements. You would just get that and use that for your geometry. So that's a good run. And if anyone ever saw the movie, it's so old by now. It's not, like 20 years old, but Lincoln. Anyone see the movie, Abraham Lincoln movie, Daniel Day-Lewis? It was like a big deal, Academy Award thing. Anyway, maybe I could bring up the scene to show. Let's see if on YouTube I can easily get, I don't even know if I have sound, but let's see. YouTube. Lincoln movie, geometry. Let's see. Here you go. I don't know if I've said.
What are you working? Well,
So this is Abraham Lincoln talking to someone.
I'm an engineer. I reckon there's machinery, but no one's done the fitting. You're an engineer. You must know Euclid's axioms and common notions. I must have in school, but I never had much of schooling. I read Euclid in the old book I borrowed. little enough it found its way here. Once learned it stayed learned. Euclid's first common notion is this: things which are equal to the same thing are equal to each other. That's a rule of mathematical reasoning. It's true because it works. Has done and always will do. In his book, Euclid says this is self-evident. You see, there it is, even in that 2,000-year-old book of mechanical law. It is a self-evident truth that things which are equal to the same thing are equal to each other. We begin with equality. It's the origin, isn't it? That balance, that's fairness. That's justice. Just read me back the last sentence of that telegram, please.
There we go. So Abraham Lincoln was known to carry around Euclid's Elements. You know,
$5.
whoops.
That's enough to make a difference in this election.
No.
If every single person watching
Oh, Obama.
pitched in $5.
Yeah, come on, Obama needs to get out there and campaign better than that. Now, so Euclid's Elements is a big deal. Second most printed book in the history of the world. And he collected all the other people. Their books were called the Elements also, the ones before Euclid's Elements. He collected them and he organized it in such a way, and he wrote a book. It's actually a book that has 13 chapters in it. The chapters are called books, so they call it the 13 books of the Elements, but each book is very short, like 40 pages each or something like that. So it's kind of like one big book, Euclid's Elements. And let me show you a little bit of what that looks like. I see. There's other math here. I don't want to look at that yet. I need to move these slides. I'm tinkering with this. This needs to go way later.
I see the triangles, right?
Yeah, that's coming. Yeah, I'm not ready for those yet, though, I realize. So Euclid's Elements begins, as Abraham Lincoln said, with before he gets to theorems and stuff, he has to lay down, what are the things that we don't have to prove? What are the things we have to start with something. And these are the 5, he starts off with 5 common notions, he says. As Lincoln said, things which equal the same thing also equal one another. What do we call that today?
Really?
Equations.
Equations. There's another word like if I'm the same age as you and you're the same age as him, and I'm the same age as him. Things equal to each other, things equal to the same thing are equal to each other. You know what? Actually, that's not right. I was thinking like transitive property. That's a little different. A equals B and B equals C, so A equals C. I guess that is. If A equals B, if B equals A and B, I'm thinking like if I tell you B equals A and B also equals C, things that are equal to the same thing, therefore, ... therefore, like that. And it's a common notion because, of course, if I'm 50 years old and you're 50 years old, then we are the same age. Yeah, that kind of idea. And then the other common notions, if you add equals to equals, the wholes are equal. So if we each have the same, if we each have $30 and someone gives us each $10, then we still have the same amount of money. And same thing, if we each have $50 and someone takes away the same amount of money from each of us, we still have the same amount of money. And this says things which coincide with one another. That's geometrically speaking. Like if I have, a triangle and a second triangle, that's literally on top of it, then they're equal. And common notion 5 says the whole is greater than the part. They're kind of like saying, like if you have a line segment, a full line segment, it's longer than a portion of it. These are the common notions because it needs to be proved. You could argue them, but he says you can't argue it because I'm not saying that we have to prove it. I'm saying we must start with something, and this is what we start with: 5 common notions. But
No, change that.
yeah. And I'm also going to post this all, but these things are, we're going to get to like the math and the proofs and stuff, but this is more sort of background. And incidentally, I found all this when you go onto Google and they have one of the most amazing websites, which is here. If you type into Google, Euclid's Elements, the first thing that will probably come up is Clark University. And what this guy did back, now it's almost 30 years ago, in 1997, he actually made Euclid's Elements as a big web page. So you don't need to buy the book because you have that. So here are the common notions. By the way, there's a bunch of definitions also. For instance, I think he defines a circle. Definition 15 says a circle is a plane figure contained by one line, he really means a curve, such that all straight lines falling upon it from one point among those lying within the figure are equal, and that point's the center. Basically, this is what lets us say that all radius are equal to each other. Now, he starts getting into what are called the postulates. So there's the common notions, the definitions, the postulates, and then come the book is mainly what's called the propositions, which are like theorems that he proves. So common notions and the postulates. Now the first 4 postulates, if you look at those, postulate 1 says if you have 2 points, you're allowed to join them and make a line segment. Which is why I asked you to bring a ruler today. He's saying you are permitted, if you have 2 points, you're allowed to draw a straight line segment. Really, it's a segment, but postulate 2. To produce a finite straight line continuously in a straight line, he's saying, let me use a different color here. So number 1 is if you have 2 points, you can join them. You're allowed to. Postulate 2 says if you have a line segment, you are allowed to extend it. Like he gives you permission to do that. Postulate 3 says that if I have a point and some kind of distance, you can kind of open up your compass and move it here and produce a circle. Postulate 3 is what allows us to use a compass, basically. You're allowed to make circles, he's saying. He gives you permission to. And postulate 4 almost seems like it should be a common notion, that all right angles are equal to each other. Of course, they're both 90 degrees. So common notion 1 would say that they're equal anyway. So it seems weird that postulate 4, it doesn't seem to fit with the other ones. It seems too obvious. But what really doesn't fit is the very famous, there's only 5 postulates. Here are the first 4.
Hold on, I need to look back.
The first 2 talk about how you can use like a straight edge. 3 is about how you can use a compass. 4 is, I don't even think 4 belongs as a postulate. I don't want to like be sacrilegious and correct Euclid, but now you want to have as few postulates as possible because you want to build from the simplest tools as much. Otherwise, people can complain and say, "Oh, I don't like this postulate or that postulate." So you're better off with the smaller set of postulates that you have, the better. And if these were the only 4 postulates, that would be great. If you could start doing geometry and building up rules and proving things about circles and triangles. But Euclid knows that he can only get so far with these 4 postulates. And he doesn't want to do it, because look at how nice and easy the 4 postulates are. But he throws in one last postulate, the famous postulate 5. Postulate 5. That if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines it produce indefinitely meet on that side on which the angle is less than the 2 right angles. I mean, that is a mouthful. Here's postulates 1 through, here's common notions. That's it. There's only 5 of them. Here's postulates 1 through 4. There's only 5 postulates. And here is postulate 5. It's called postulate 5. It's called the so-called the parallel postulate. And it basically means that if you have 2 lines, like that, and you draw a 3rd line across it, so you have these 3 lines. 2 lines, the first 2, may or may not be parallel, but the 3rd line crosses both of them.
Is it perpendicular to the first one?
No, it's not perpendicular. That's a great question. It's not necessarily perpendicular to the first one. Let me make that. What he's saying is if you take these 2 angles, I should make that one. Yes, it's going to be related to that. If this is 50, whoops. He's saying if this is 50 and this is 110, he's saying that if those don't add up to 180, they're not parallel. So if they did add up to 180, let me go like that. So they are parallel because 50 plus 130 equals 180. And here, they are not parallel because 50 plus 110 is not 180. So that is a mouthful of postulate 5. And like in history of math, I can actually imagine a history of math course where you hardly do any math, and you really just like learn this, like the important moments of math. And this would be one of the most important moments ever in math. The realization that he can't prove this without, he has to just tell you, he has to just say, this is one of our rules, I'm telling you it's true.
for thousands of years, people tried to prove it and say, you know what, do you really need to make this a thing that we have to just take as unproved? And for thousands of years, people tried to prove the parallel postulate, and they weren't able to. And then eventually, in like the 1800s, they realized that if you don't accept the parallel postulate, you can still do different types of geometry that would be like what's called spherical geometry or hyperbolic. There's a whole type of geometry where this wouldn't be true, and it would be okay. So it is. So he had to postulate it because it's not actually necessarily true. It's just true for flat surfaces, but it's not true for like spheres and things like that. So, but that's the parallel postulate. That's a big deal of a thing. Like just to like, you know, if you type in, you know, the parallel postulate. Okay, first thing you get is Wikipedia. The parallel postulate, also called Euclid's fifth postulate, because here's the fifth postulate, is a distinctive axiom. It says this: equivalent properties, history, converse, criticism. Oh, this isn't as long of a page as I would have expected. Parallel postulate's a big deal. But I show you this because it's almost like, to me, almost like funny. Like when I look at postulates 1 through 4, and then this like monstrous parallel postulate. But now you know what the parallel postulate is. Someone mentioned alternate interior angles. It is kind of like that. They actually call these same side interior, like alternate interiors when it makes like a Z. But they're saying if these two angles add up to 180, they're parallel. But if they add up to less than 180, they're going to intersect eventually. Okay. After the 5 postulates, we end up with the 465 propositions. And we only do like 10 of them maybe, you know, like rules. Like we've already actually done a few of them. 465 propositions organized into 13 books. And I'm going to list off a few of them because we actually have already experienced some of them because the Thales ones. So for instance, book 1, proposition 5, and that's just how we always do Roman numeral for the book and a regular number for what proposition number it is. Book 1, proposition 5 is the one that says if the isosceles in an isosceles triangle, the base angles are congruent. So that was one of Thales. Another one is book 1, proposition 15. That was the one that says vertical angles are equal. Book 1, whoops, that's a nice color, but book 1, proposition 31. Sorry. Book 3, proposition 31. What's the other theorem?
That's book 3.
Yeah, book 3. Yeah, Roman numeral 3, 31.
What is that?
Thales theorem, that if you have a triangle with a diameter, the diameter is one side of the triangle, it will be guaranteed to be a right angle. So the Thales theorems were and let me hold on, I have a few more in here.
So does this book just keep like getting bigger and bigger? Are all those people accredited in there? Like,
Oh, no. No, he doesn't mention Thales in there at all. I mean, he doesn't mention anybody.
Okay.
It's just
That's
really,
just
just goes from one to the next to the next. Okay, so 1:5, 1:15. Book 1. And by the way, it's not like you have to memorize anything. I just want to tell you that everything that we've done so far has a location in Euclid's Elements. Book 1, Proposition 32, has that the angles add up to 180. And it also has, as part of it, the exterior angle. Actually, why don't I write it this way? Okay. So everything that we've done so far has a location. These Roman numerals, I think you should memorize them. So in geometry, when they would like do a proof, and you might remember from geometry, you had to write down. Then people remember statements, reasons. The reasons would just be Roman numeral 1. They would just refer back to the name. So people didn't have to memorize. They didn't have to write a vertical angles or congruence. They would just write 1.15, and everyone knew that's what it was. So like the Bible with like chapter, with verse. Chapter, verse, book, how do you say it? Verse, chapter, verse. Like chapter and verse in the Bible, which book in Euclid's Elements and which proposition are we talking about? So yes, I'm showing you the different numbers because this is what we've learned so far. This is everything we've done so far today. We've seen the 4 Thales theorems, and we haven't proved anything. The only thing we've proved is we proved this one. Now Euclid proves all these things. He proves all these things separately. I'm going to add to our collection 2 more theorems. For 129, let me come over here for a second. It's kind of like postulate 5. But if these are parallel, and you draw the third line, so it looks like an equal sign, like a not equal to sign. It's got 2 parallel. So here I'm actually telling you these lines are definitely parallel. And if I told you this was a 50-degree angle, what would that angle need to be, you think? So talk to your neighbor about it for a moment. So I'm telling you they're parallel. They are parallel. What do you think about that angle, that x angle? Which okay, what do you think?
Also, just when it's going to be 130.
Then what do you guys think that angle is?
Yes. Okay.
Why do you think 50?
I have a card that's like 180 minus 50. So you know that the angle above it is 130.
Yeah, that's right.
180 minus 130.
That's exactly right. We could use that postulate 5 to say this must be 130, which makes this thing must be 50. But you now are permitted, if you ever see, it looks like a letter Z. If you see a Z, you can just jump straight to the 2 angles in the Z are equal to each other. That's called, someone said it back here before, the name for those. Those are alternate interior. So now we know those as alternate interior angles. We're going to need this later on. So if you ever see like a letter Z, these angles will definitely be, only if we know that they're parallel. If we're told we have parallel lines, the z, the alternate interiors they call them, are equal to each other. And that I'm going to give a name to. That's book 1, proposition 29. So we're going to be allowed to just say it. So here is our collection of 5 theorems. The only one we actually proved was this one. And we assumed this one and the 180 degrees thing. We assumed these two to prove that. That's a nice collection, though. See, I'm trying to give us what's the minimal tools. I hope you're not overwhelmed by these 5, really 6 theorems, because here's 132 has a exterior angle theorem and that in it. So these 465 propositions, half of them, or I should say half, some of them are theorems, like these. Proving in a triangle this is true, in a circle this is true. So the propositions are, there's 2 main types, 2 types of propositions. There are like theorems, new rules that we prove, but a big chunk of them are what are called constructions. Constructions are a recipe for using a compass and a ruler to produce a picture, like a shape that has properties. And the theorems are used to prove that the construction you made actually did make the thing that you said.
You said it's a recipe to create.
To create something, like make an equilateral triangle is one of them. So it's a step-by-step, do this, do this, do this, out comes the shape. But how do you know that the shape is what they said? The theorems prove about the shapes. And throughout Euclid's Elements, it's basically a book about constructions. And the theorems are just there so that you could prove that the construction actually works. Throughout the whole book, every few propositions, there's a new construction that utilizes the theorems that had just been proved. And then they get more theorems, like where he's going with this. Another construction, which conveniently uses the theorems he just proved, more theorems, more complicated construction. So Euclid's Elements, to me, is mainly a book about how to use compass and straight edge to produce cool-looking stuff. And that's why we brought the compass and straight edge today. So let's do a break now, because when we come back, we spend the rest of the time doing... we need a 5-minute break. There's a few other things I have to say before we get the compass and straight edge going. Okay, so everyone relax. Take 5. You get to see people in person. It reminds me of that. You know, see movie Die Hard. He's like in the building. He's a hostage, you know, and he's talking to a policeman out on the street for the whole time. And at the end, they finally meet at the end. No, you know that movie?
I know.
Trivia question. What's the name of the policeman? Have you seen the movie recently?
Not recently. He was the guy in Family Matters.
That's right. I think it's Al. That they meet at the end. That's a great movie. They like look at each other, help you save his life, you know. Okay, so totally acquaint yourself with your classmates.
Professor, I left in the middle of class because I parked in a totally zone.
Did you get, yeah,
I had to move my car right in.
okay, you're able to move it, okay?
Yeah, it took me like a half hour to find parking. I emailed you actually.
Okay, that's no problem at all.
Um,
Yes, so it's, yeah, parking here is, fortunately, just have to come in the 3 times.
yeah.
Well, I'll tell you, it is hard to come in, you know, commuting, but people learn a lot more in person, and also
Yeah, I agree.
seeing like the other people, there's a lot more energy, interaction. Teaching on Zoom is not
It's not fun.
not fun. I'm actually so tired after a Zoom
Yeah.
lesson. I'm exhausted.
Weird.
And here, I'll leave here, I'll be exhilarated. I'm not tired at all after teaching in person.
Yeah, I find myself taking naps.
Yeah.
Like, I was so tired just sitting in front of the computer.
Yeah. If anyone needs a compass, oh yeah.
Oh, I read some of your comments.
Oh, now, Letitia just went and bought one for less than $2 in the school
I
store.
was gonna, oh, downstairs?
Yeah, like right here. Were there a bunch?
Yeah.
Yeah. So you could grab one if you want. You don't really need it for what we're doing, because we're only doing, we're doing 4 constructions. You could survive with that. You know, there must be compasses in here. They have every possible manipulative, so let's look.
It's alphabetized.
No. Thank you. So let's look at C. Wow.
Yeah, these are manipulative.
They have like every manipulative.
What are you, the room next door?
Oh, yeah, okay, okay.
Map in the city.
Uh-huh.
I have compasses.
You would think one of these boxes, it's like. Oh, maybe question?
Yeah, but I was gonna ask, I know that you did something like this, right? And you said that these 4 shapes can eventually make.
5.
Right, sorry, I said 4. That these 5 can make this large square.
Yeah.
I was wondering, because there's this activity that I have already done with my students, in which they have to, I don't have the link here, but they can create a square
Mhm.
out of 5 shapes.
Uh-huh.
Wow. So I was thinking if I can make this in real life, it's kind of like a puzzle.
Mm-hmm. Yep.
And if so, what are the numbers that I can use?
Mm-hmm. That's an excellent question. So you have to make a right triangle, right? Right triangle. This is the 3 squares. Now you would find the center of the square by doing the 2 diagonals, and then this line would be parallel to this, and that would be perpendicular. So you could make this real easily. This is the actual center of this square, but this line is perfectly vertical. So
Okay.
that's how you make these trapezoids, or whatever they are, quadrilaterals. So you can make it that way.
I'll try and see.
Yeah, so,
I'll try to make a small version, and see, because I know that this probably has to do a lot with like numbers and.
oh, the numbers wouldn't matter so much, like I mean, as long as this is the right triangle,
Okay.
these things will just work out nicely. If you want to make it like a 3, 4, 5 triangle, you could. You know, you make 3, 4, 5, and then you draw. You wouldn't have to draw this thing. It would just be these 2.
Oh, okay.
Yeah.
And then these 2 will
They
make
would
this.
fit. Yeah, that would be really hard to draw this thing,
Mm-hmm.
because this thing, it looks to me like. No, this would be hard to draw because you would pretty much have to say, okay, this line came from. This is like. It's hard, right? Because, let's see, this line would be copied over there. Wherever that line became is where you cut that thing off. So you get these points on the edge, whoops, and then when you connect to them. But no, I wouldn't make this bottom one, I would just make the top.
Okay. Thank you.
Well,
I don't think I have a minute.
yeah.
I just didn't understand this problem at all. The double doors one.
Oh, you're trying to do more?
We didn't have to do that one.
Oh, okay.
No, we don't have to do the 6.
Oh, okay,
So,
so 6, like the first 6?
Yeah.
Oh.
Yeah, that other stuff was just like for reference. No, it's the total.
Wait, okay, I thought that was a lot of homework.
Oh, no, that you guys do, oh, no.
Yeah.
Oh, my God, no. No, you said to do the, no, not even the, you said to do, wait.
I printed it.
I got you, I better explain it. No, you didn't do any of those.
Oh.
It was just the 6 that was in class, and then I changed the numbers around to make 6 other questions like those.
It was in like.
Let me take that. Yeah, this is the homework.
Oh, okay.
This is the homework. These are the original questions. Meaning like, you have to, oh wait, let me correct. Oh, actually. So no, you went way above and beyond because these questions are very hard.
Yeah, I didn't understand the door cell thing. I was like, oh, what is it?
Oh, the door. You know what? Do I have a diagram for it? You can see I drew. It's like a trapezoid of some sort. Where is that? There. Yeah, I think the idea was the doors. They do like the doors, I think. They like swing.
Yeah, because that's
Yeah, it like swings this way, and this one's, the doors are like this, and they swung, but there's like a thing here that like stops them from opening up all the way.
Okay.
So it turns into this like trapezoid thing.
Oh, okay.
But yeah, you only have to do, no, the homework, this was the homework.
Okay, that was
Those
like,
those other
this is
ones
the
were.
craziest homework.
Yeah, no, those
The
other
rest of
ones.
them were the things you were talking about, right?
Which one?
Because afterwards, it's like it lists everything.
Yeah, that's just for reference. That's just like, it's a look at. No, the homework was literally the 6 questions from yesterday, just with the numbers changed.
Yes, I finished it,
And
but
then,
I didn't post it. Have to post it.
oh yeah, you have time.
This was fun though. I was like,
Well, it is really interesting because there's this collection of cool questions that have been around for thousands of years that have been like mainly forgotten. Like those questions are not any. There's one with like a log that's in the wall, but it's so weird they like put the log into the wall like horizontally.
Yeah, oh yeah, that's what, like 9 was something about a log drilling with. Like,
Yeah.
And I was like, I don't even know what that means.
I drew the picture of it to show that like the log is literally like here's the wall, and the log is like just put into the wall sideways.
Yeah. But then I have a question. Did I do these right then? Was that the tree and the gate?
Oh my God, yes! Wow.
Oh.
Yeah,
yes.
yeah.
I was like,
She did the other. Yeah.
it was, I didn't understand what they were saying.
I have an
I was
answer.
like, yeah, it's like that was a lot of homework.
Yeah, that would be a lot. Well, you
So
definitely.
these are the ones, right?
Just those 6, yeah.
I do my tree.
Yes, the tree, nice tree.
The pool,
The lake, yeah, the pond. Those,
I redid the construction of it to get that.
the one, the sliding pole, and there's the 2 guys walking in a southern and eastward direction.
Now,
It's great.
okay,
Yeah, this is exactly.
okay. Yeah, I didn't go any further. I was like, what? No.
Yeah, I kept looking through the notes. I was like, is this really all the whole? This is like all.
No, that would be-
I said 20. I
No,
said
if you
6.
did that, I would say the first time I did those, it took me a really long time, but I didn't have diagrams. So you went way above and beyond.
Yeah, I thought I was doing like college physics homework or something like that.
Yeah, because when they started talking about circular log, I said, that's not
The
a
log,
log.
yeah, the log.
That's not how it works.
They put the log into the wall like this, like a big log, it just like
Here's a
wedged
Z.
into the wall.
Here's a Z.
There is either.
There's like the divine wrapped around the tree. I figured that out. I was like,
Oh,
I did
that one's hard,
Yeah.
the vine around the tree.
But I figured that out. You flatten it, and then you're making a
It becomes a big triangle.
Yeah.
2 in there?
Okay, everyone, now we're ready
She wants to
for.
go get her.
Yeah, you got some more.
Oh, wow, you went and bought some?
Yeah.
Oh, okay. They don't need.
Whoever wants one.
Wow, that was,
and they were like $2 each. So if anyone's missing a compass, why don't you buy from Stephanie?
The bookstore on the first floor.
Oh.
She's selling them for $3 each.
There's a bookstore, but no one has cash.
Yes, there's a bookstore downstairs. When you first come in the NAC on the ground floor, it's to the right.
Oh, okay.
Okay, so does anyone need a compass now? So we're going to learn for either 3 or 4. It depends if I have time for the 4th one. I might just have time for 3. Probably just 3. Constructions. And the very first one is the very first one, the very good way the entire youth development starts. There's 465 propositions. But only one is the first, literally, book 1, proposition 1. The goal is to construct an equilateral triangle. They'll get on a given line segment. So you've got a line segment. So on your paper, you could go ahead and draw a line. Use your ruler to draw a line segment of whatever length. Actually, why not just, if it's a ruler, you can just make it whatever number of inches you want so that you can verify at the end that it's an equilateral triangle. Now, it's true, back in those days, they always say compass and straight edge, not compass and ruler. Because technically, the markings on the ruler could be used to cheat. So, technically, a straight edge was literally a straight edge, a ruler with no markings on it. And they restricted themselves to these tools. Not because they didn't have rulers with markings on them, and not because they didn't have protractors. They had all kinds of things. They had something called flexible ruler. They had all kinds of tools. But the goal was of this, the rules of this game were, what if I restrict myself to the most pure 2 things? The ability to make lines and the ability to make circles. How far can I go with just those? So if anyone ever thought, oh, they weren't very sophisticated, all they had was a compass and a straight edge. No, they were so sophisticated that they rejected the tool. They said, why should I have a protractor? That's cheating if I can accomplish this with no protractor. So it's sophisticated. So I'm going to teach you how to do this. And it only takes like a minute or a few seconds to do it. So, let's see, clear. So step 1. Maybe I have to use, okay, so you have a line. Now you take your compass and you put the points onto one endpoint of the line segment, and you open, oops, you'll want to make your line small enough that the compass can open to that length. So, okay, so move the pointy part of the compass onto one and put the pencil onto the other. And then he says to make a full circle. But the truth is, you don't need to make a full circle. You could just make, oops. Let me try this again. Let me just get the hang of this. So you go like this, and like that. Now you truly only need to make a small portion of the circle, which is an arc. You only need to I see, this is gonna draw, how do I wanna stop it from drawing, I want it to like, but that's all right. You only really need to make a small portion, but Euclid actually said to make the full circle. So that's step one. Why don't you go ahead and make the full circle, like Euclid. Now, you lift the compass, and you put the pointy part on the other endpoint of the original line segment. And just to make sure the compass didn't change size, go ahead and put the pencil part on the other one, on the endpoint. So basically, put the pointy part of the compass on one endpoint, the pencil point on the other, made a circle. Then you swapped it. You took your compass, lifted it, and you put the pointy part of the compass on the other endpoint and the pencil on the other. And then go ahead and make, let's go ahead and make a full circle.
And so long as I use this.
So everyone go ahead and do this. So your picture should look like this. You have the line segments in the middle, and you have the two circles. Now what you do is from the point where the top point where the two circles intersect, use your ruler now to make a line segment joining this intersection point with the end points of the line, and then again from that point to the end point of the other line. So two circles, and then two line segments.
I haven't used this in a long time.
Okay, so that's looking good. Some of these compasses, that aren't the cheaper ones, they slip, the size changes, the little pointy part, slips. But go ahead and make two circles, and then the top intersection points of the two circles, that's going to be the vertex of the triangle we made. And we stop there. Okay, so go ahead and do that. And again, today I'm pretty sure we're just going to do three constructions today. I'm gonna hold off because the fourth one is, I realize I'll have to chop the last question off the homework also. No big deal. Okay, so on everyone's paper, we should see this triangle. And now the question is, yes, we see a triangle here. There's a red triangle. It looks equilateral, but how do you know? How do you know it's equilateral? Talk to your neighbors about that. It's a fun question. Like, that's a good-looking triangle, but are you positive?
The writing is all the same.
Oh, there you go. Now you. But someone that is going to be the reason. But so talk to your neighbor. Letitia said it has to do with the radii. How so? How do you know that all three of these sides must be equal to each other? Talk to your neighbors about it for a moment.
Because according to
Like
the postulate, look, according to the postulate,
That's right, because there's no
postulate number 3.
That's right. What postulate 3?
Because of that.
So you can make a circle with the radius,
Yeah.
Yeah, there's no problem. He has no theorems yet at that point. It's literally book 1, proposition 1, so there's nothing except the definitions and those postulates. So Letitia, you said because radii. What do you mean by that? Like, I'm going to stick some letters on this picture. I think if I put some letters, it will be easier to discuss. Okay, talk to me, use like AB, AC, we have 3 line
Because
segments now.
the radii AB
yes.
is equal to the radii for BA.
Wait, BA and AB, yes, that's right, BA and AB, these 2 circles are the same radius, yes. How does that get AC and those other 2 lines involved?
Because according to the postulate, when you draw a line from any line segment, isn't it equal?
From the center to
Okay.
the circle, yeah.
So that means that they're equal.
What's equal? When you say they?
The
Because
AC,
AC,
BC
yes.
are equal because you drew it from the radii of AB and BA.
That's right. AB, all right, it's this way. AB and AC are equal because they're radii of the same, of circle A. On the other hand, BA, I like that way of talking about it, BA and BC are equal because they're both radii of the circle on the right. And then combination 1, things equal to the same thing or equal to each other. And that makes all 3 things equal to each other. And this thing is definitely equilateral. And
That was really hard.
It's-
I understand it.
it gives you a
I
headache.
can't write it out.
You know, it's funny you should say that. Let's look at how Euclid writes this up. We're not going to have to write up proofs, you know, but you might be interested, like, how does he describe it? Let's see. It's pretty wordy, Euclid's Elements, actually. Describe circle BCD with center A and radius AB. Again, describe the circle ACE with center B and radius BA. Join. Here's his proof. Now, since the point A is the center of circle CDB, therefore AC equals AB. This is using definition. Postulate 1. Oh, first, postulate 1 and 3 allow him to draw the stuff. Definition, this is definition of a circle. Definition 15 is circle has equal radii. But AC was proved equal to AB, therefore each of the straight lines AC, BC equals AB. And things which equal the same thing equal one another. Common notion 1, Abraham Lincoln. And that's it. So we're only doing 3 constructions today. That's already one of them. Now, the reason we're only doing 3 constructions is because I have more to explain before we could do the second construction. Now, this is an extremely important concept right now that if you took geometry back in the day, you might vaguely remember there were a lot of triangles, and you had to often prove triangles equal to each other. So, first thing I just want to mention, here's 2 triangles. You know, are they congruent? Are they not congruent? We don't know from this. Then I start writing in
One bigger than another?
yeah, this isn't not drawn to scale. Let's say here. Wait, let me draw. This is all just. This isn't going to be drawn to scale so much, but I just want to like make a point here with 70, 80. Okay. I measured everything. Triangle has 6 pieces, 3 angles, 3 sides. So yes, these triangles are congruent. Every single thing of them is congruent to as a partner that's congruent. Now if I take You might argue that if I tried this, if I took a triangle, if I reflected this triangle, so the 30 degrees was here, and the 70 degrees was there. We could probably have a whole argument about, like, for sure these two are congruent. Like every single piece is exactly the same. But if I flip it, is it still accurate to say that the first triangle is congruent to the one on the third one? Does anyone feel strongly one way or the other? Still, are they still congruent or?
Yes.
Yes. And yes, congruent counts even if it's like flipped, as long as the 6 pieces, the 3 sides are equal. And the angles, like the angle between the 8 and the 10 is 30, the angle between the 8 and the 10 is 30, the angle between the 8 and the 5 is 80. So yes. So triangles are congruent if every single piece is congruent to every single piece. So I'm going to say S, 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 A. In other words, all 3 sides and all 3 angles are equal to each other. So the triangles are definitely congruent. Now, I need to make a copy. You know what I need? I need the clone page as one of my tools. I need a couple of clones in this page. Okay. Now, what if I don't have all this information? What if that's all I have? I have 5 pieces that I know are equal, but I'm not sure about the 6th piece. Is that enough?
Yes.
It is still enough. I'm just gonna write down. Still okay. What if I? Well, I'll leave that. What if I do that? Actually, what if I do that? Are we certain that these 2 triangles are congruent?
Well, if you think about what they said in Abraham,
Oh, are things equal?
yeah,
Yeah. So do you think they are? Because
if one side equals the other side,
we have 2 sides. Yeah.
then all sides are equal.
But check this out. Here's a counterexample. What if I go like this on the same picture?
And then
That red triangle still has 5 as a side, and it has the angle 70. But that red triangle, so is definitely different from the one on the left. So sometimes there's not enough information. Like they might be equal, but they might not be. So I'm going to write down.
what about notion 1?
Well, notion 1 is saying that if this equals 5, and there was a third thing that equals 5, that they'd all 3 be equal to each other. But notion 1 is not talking about triangles and how much information. You know what would be? Let's look at an extreme example. If all I knew about the two triangles was that they had one side equal. Basically, you can make many different triangles that have a side of 4. But apparently, I can only make one triangle that has all these 6 things in them. So we're trying to figure out what is sort of the minimal amount of stuff that I could know where the triangles, we could say for certainty, like over here, we still knew the triangles were congruent, even though we didn't know about all 6 pieces. And here, it was like not enough information.
So you need 3 pieces?
Well, it depends which 3 pieces. So I'm going to tell you that 3 pieces are enough in this situation, where 2 of the sides are equal, like you have 2 sides equal, and specifically 1 angle, but the angle that's actually formed by the 2 sides. If that happens, then yes, they are congruent. And this one is called side angle side postulate. Otherwise known as SAS. Sure, I have the right. And in Euclid's Elements, he describes this and says it as Book 1, Proposition 4. Euclid says that if you have 2 triangles, and I'll give you a second to. If you have 2 triangles, and you know for sure the 2 sides are equal, and the angle between those sides is also equal, you can be certain that the whole triangle is equal to the whole triangle, and that the other pieces, the other 3, that are going to be equal also. Let me go to another fresh page. Just, I'm still on this topic, this idea. So the idea, I guess, is this. That's 40. That's 10. So this would be, I like this as like a test question. Can we definitively say what that question mark is or not?
Yes,
It was that?
because the side angle sides are equal, so all other things are equal.
That's right. So yes, you can fill that in because SAS, I'm going to say the triangles are congruent. This is the symbol for congruent. So SAS says the triangles are congruent, and once they're congruent, all the other pieces also work. You might remember from back in the day, they would say they'd use the letters CPCTC, which meant corresponding parts of congruent triangles are congruent. Basically, it just means that any other piece, once those 3 pieces are in place, all the other pieces you can be sure about also. So that's Book 1, Proposition 4. Now what's funny is that here I said postulate, but it's listed as a proposition in Euclid's Elements. Postulate is something they say, hey, just trust me, it's true. Postulate. Proposition is something that you prove from the other postulates. So which one is it? Is it a postulate or a proposition? Well, Euclid says that he proved it. Proposition 4. Except his proof is terrible. It should have been a postulate. The way this proof is a terrible proof. He says we have two sides, AB and AC equal, and we have the angle up here, BAC and EDF. And then what does he say? He says, I say the base also equals the base, and everything else is equal. And his reason is that if triangle ABC was superimposed, if you literally put it on top of this one, and point A is on here, this proof is garbage. You know, it's not a proof at all. It's just basically saying it's obvious. He's saying, which it's not obvious, but this is not a good proof. It's really, that's why most people call it the SAS postulate, because you really can't prove it from. You really can't prove it. You have to pretty much start with it. Now there are there are two others. So it turns out, I'm going to tell you what they are. Oops, I'd like to have all that stuff written in, but I'm going to remove these three things. If the three sides equal the three sides, and you don't know anything about the angles, it's true that the triangles have to be congruent. So that's enough information. So I'm going to say yes by what's called the side. SSS. And just so you know, Euclid side is book 1, proposition 8. What's funny about that one, so he proved that if you know three sides are equal, you know all the angles are equal also. And if you're wondering, like, how do I like to make up, test questions? And I say, is there enough information, yes or no? Because the answer could, I could make up one where the answer is no.
What is this called?
The side postulate. In other words, if all the sides are equal, you can be sure that the angles also are equal.
Can this be proven?
That's an excellent question. If you go into Euclid Elements and you go to book 1, proposition 8, if two triangles have two sides equal and also have the base equal to the base, that's funny. Instead of saying all three sides, they have the two sides and the base, then they also have the angles equal. Well, he uses 1/7. I gotta look at what 1/7 was. I thought he was going to use given two straight lines. He does 7. But 7 is based on the equilateral triangle. Okay, so the answer to your question is, you could prove SSS from if you use SAS as one of your reasons. So it can be proved, but something has to be postulate. So you can't prove it from scratch, no. But if you get to cheat and use the SAS, which wasn't really proved, then you can. So this one, the answer is 40. Because, yes, the triangles are congruent. So so far we have SSS, SAS is one way to prove triangles congruence, and SSS is another way, and there is a third way. There's just going to be 3 for our purposes. We only need 3. And the last one, oops, I keep doing that. These two, yeah. This one's also okay. This one's called ASA. Angle, side angle. So if those three pieces, and by the way, that's book 1, proposition 26. To summarize, there are 3 main ways that you could know the 2 triangles are congruent, even if you only have 3 pieces matching. And just to summarize on one sheet, if you have this situation, that's called SAS, 2 sides and the angle between. If you have this situation, they're congruent by SSS, side, side, side. And finally, ASA. But not, you might get tempted into thinking, for instance, all right, maybe, but it's not SAS. Sorry, it's not ASA, even though there's 2 angles, but the side has to be the one that's between the 2 angles. Maybe, but maybe not. Because ASA means literally the side that matches must be the one that's between the 2 angles. So this is, I wanted to show you how that works, because you took geometry so many years ago, and I think I had this really good way of showing you, like, all 6 pieces, we're sure, but we kind of remove a piece until, like, it almost becomes impossible to know if they're equal, but then we add pieces back in. These are the 3 things.
Say that again?
What's that?
That
Oh, just
does not.
maybe, but maybe not. The reason, even though this has 2 angles equal and a side equal, they may not be congruent because this side has to be, it should have been this bottom side. ASA doesn't just mean, oh, there's 2 angles equal and 1 side, but the side must be the between the 2 angles. Now we're ready to do something with this because we have our second construction. We only have 3 constructions today. Construction 2, how to make an angle bisector. I want you to, on your paper, draw an angle. Make an angle. I usually make it a acute angle, but draw an angle of whatever size you want. And I'm going to come over here with this thing.
Under 180, right?
Under 90.
Under 90, okay.
So I'm just going to make a random line segment. Yeah, random line segment and a second random line segment. Okay, step 1. Move your compass so that the point is on the vertex of the angle. And open the compass up. It doesn't really matter how big to make it, but don't make it so big. We want to make an arc that hits both of the lines, so this would be like not good, but if I go like that, so basically make an arc that that goes through the two sides of the angle. It just needs to be big enough to go through the two sides of the angle. And now, you are going to, with your ruler, connect those two intersection points. Like that. Now, that line, this line segment here, on this line segment, you're going to go and create an equilateral triangle, which was our first construction. Which is a little hard because it's sideways, but of course you can turn your paper, but I'm going to come over here and go like that. Oops, bad news, I didn't lock my compass. Let me try this again. So I go like that, lock the compass. I'm not making the full circle, because I don't need the whole circle, I'm just making the portion of it that I need. This, I didn't make the whole circle because it starts getting really, really, really busy with the whole circle.
So you could have this at anything?
Well, no, I opened it up to the size of this line segment. Because remember when we made the equilateral triangle, we opened it up to this size and made a full circle, and then we swapped it and made another full circle. But since I only really care about getting the intersection of the two circles, I just made enough of those circles.
And you put it here on the next point?
Yes, maybe this will be better. I am. You know what I'm going to do, just so that it's more consistent with what I have been showing you? I'm going to make the entire circle, even though it's going to make the picture really busy. Let me move this. Here, I'm going to do the full circle, like I did before.
I did it. That was busy.
This is pretty busy.
Is this what you're looking for right
Here you go. Let me go ahead and make my full equilateral triangle now.
Oh, yeah. Okay. I did it
Okay, so your thing looks like that.
right. Mm-hmm.
So it's pretty busy. We're going to make one last line though. From the vertex of the equilateral triangle. Oops. From the vertex of the equilateral triangle, connect it to the vertex of the angle. Okay, so it's busy looking. I know. Looks like that. But that last line you drew is an angle bisector. And I'm want to show you why. I want you to pay close attention to this red triangle, sort of an obtuse triangle, and this blue triangle. If those triangles are congruent, then these two angles here will be equal, and that would make an angle bisector, because the two angles are equal. The question is, why should that red triangle be congruent to the blue triangle? Go ahead, talk to your neighbors about that for a second. Why should that red triangle be congruent to the blue one? It's either going to be SSS, ASA, or SSS. Those are the only three possibilities. So which of the three triangle postulates would verify that the red and the blue are congruent to each other? Is it because of SAS, ASA, or is it because of ASA? One of these three is the reason that the red and blue triangles are congruent. Talk to your neighbors. Which one do you think it is? Is that because you think the angles have to be, even though we're making an angle bisector, we can't assume that we know it's an angle bisector. So we can't say for sure that those two angles on the left are equal.
Angle, side, angle.
We have a circle, you know, so we have to be just the inverse of so that's the same side and the
What do you think it is?
I was just looking at
Is it, which angle do you think is equal? Like which angle are you positive?
Angle, look, let me share this on the straight line.
Oh, SSS.
Yes.
Oh, that was right.
Okay.
I thought you said SAS. Okay, Stephanie, you said, what, you want to justify your SSS?
Not really.
Okay, Mary Ellen? If I throw some letters on here,
Yeah, we don't radius.
there's a lot, yes. There's a lot of radiuses. BC and CD, they're part of that equilateral triangle. And AB and AD are part of the bigger circle. But that's only SS. That's only two sides. What do you notice? AC and CA coincide. So I'll just go like this. That third one is equal to itself. So SSS is the answer. And then because those two things are equal, we can then say that all the things are equal.
Which one is this?
Oh, I wrote the wrong thing.
Oh, hi. Huh?
That's it.
Okay.
So once we have those three pieces established, the other pieces are also equal, including so these are equal also. So it's an angle bisector, because if they're equal, that's what makes it an angle bisector. If the two things are equal, it's an angle bisector. That's what definition of angle bisector is. We cut it into two equal pieces. So it's very clever. Now, I hope you don't mind. I'm going to go 5 over because we started like 10 or 15 minutes late, sort of waiting for people to get here. So this last one won't take long. It's not. We're skipping the fourth one. The fourth one is going to take like a half hour. So that one we'll do next class period. The last one is midpoint of a line segment. And for this one, I'm going to go like this. I'm going to say Step one. Make the equilateral triangle. Now, of course, that would take a whole, 2 circles and all that, but let's just say that you made it. You made the circles, and then you erased them afterwards. Like you made the construction lines really light, so that you could just have equilateral triangle. Because that really would require 2 other circles, but I'm just pretending I already made those circles. We know we can do it because that was the first construction. Step 2, there's only 2 steps. Bisect angle ACB, which was the second construction. Now I know bisecting an angle requires a circle, a line, 2 other circles to make the equilateral triangle and a line. But let's just pretend that we made all that stuff. So this picture would be really, really busy. But when it was all done, it would look like that.
Second what?
Oh, second construction. That was the thing, really the 3 constructions. So the first construction was make equilateral triangle, which required 2 circles and 2 lines. The second construction required 3 circles, so it was annoying. But let's say I did it all and then I erased all the circles, my picture would look like this. Because I made an angle because CZ's angle bisector, these 2 angles are equal. And because this whole triangle is equilateral, these 2 sides are equal. So my question is, by which postulate is this green triangle congruent to this purple triangle? Is it SAS? Is it SSS? Or is it ASA? Talk to your neighbor.
You said congruent.
Okay, which one do you think? You think what? You think SAS?
Yeah.
Yes. What's the third side then for the SAS? Because all we have there is one.
But it's because the triangle, seemed that the triangle was cut in half.
Well, that's true. It seems that way, but if you're using SAS, you're right. And it is cut. It seems like it's cut in half, but we need to say SAS, ASA, or SSS. So why, if it's not enough to seem like it's cut in half, although you're right, it is. What you going to say, Kelsey?
Yeah, that side that they share.
CZ is a shared side, so let's go like that. CZ is part of both triangles, which makes the 2 triangles congruent, which means that those other pieces are congruent also. And if AD equals, so I'll write this, AD is congruent to DB by, I know these letters might bring back bad memories for people, CP, CTC. That's just a fancy way of saying if these 3 pieces are equal, the other 3 pieces are equal, and this is one of them. And that makes it a midpoint. That's it. That's midpoint. But if
It says CP.
CP, we don't have to actually even say that. Because it's since the triangles are congruent. Once we know the triangles are congruent, we can talk about the other three pieces. Like these three pieces told me the triangles are congruent, so now I know the other pieces are equal also, including these two that get me the midpoint. Let's forget it. Don't worry about perpendicular bisector. That's not important for our purposes. Midpoints. So now we've done today, it's really a lot, we're done. The homework's kind of funny because I want you to do the three constructions, just practice them. The three constructions, yeah. Equilateral triangle, angle bisector, which involves an equilateral triangle, and midpoint, which involves an equilateral triangle and an angle bisector, which itself has an angle, equilateral triangle. So you'll practice the three constructions. Yes?
Is it okay to do the angle bisector construction without drawing all the circles? Because it being that busy is kind of confusing to me.
So let's see, what would be the minimal? Here's an angle bisector. Some people go like this. Let me, so what's you're asking, what's sort of the minimal?
Yeah.
So here's the minimal angle bisector. Those are two arcs of that first circle. That's the minimal. In other words, I literally just drew the portions of the circles that were important. Wait, that's not the angle. Yeah, yes. Because, sorry, this is in the wrong spot though. That's the minimal. This point here is the top point of the equilateral triangle. Here, I'm going to put it in red.
You want to see the triangle?
No, don't even need to see the triangle. Well, he was asking what's the minimal.
Yeah.
So here's the line segments that were removed. Here's
We don't have to bring the protractors to the final, do we?
oh, compass? No. No, you'll see on the homework I get questions about it. But your question was what's the minimal? The minimal was these 6, 1, 2, those 4 plus the line. That's minimal for angle bisector.
Okay.
And minimal for equilateral triangle would be that. And minimal for midpoints would be, wait, I gotta get myself.
And drawing the...
Yeah, we actually have to draw. And then, so there's minimal, but drawing more might help you. Okay, well, I'm really glad. See, I was talking before this group. Zoom classes is really, if you taught during the pandemic. I was like, oh great, I'll do some remote because of course I don't have to commute. But I'm like exhausted after the remote class, and I feel very energized because I saw a lot of good energy and makes me. But so we'll be in person 1 week from today also. Makes me kind of regret not saying to come in more. Of course, you might like doing it at home. I don't know, but I'm not going to change the thing. We'll see each other in person next Thursday, like today, and I'll see everybody on Monday. I think it will make the Monday class more fun now that we've gotten to meet each other in person. So,